Great. So let me just start out by congratulating the other poster winner, Louise and Jacob. And I also want to thank the judges that took their time during the precious coffee breaks to go talk with us, evaluate all the posters. So my name is Charles Cadieux. I'm a third-year PhD student at Université de Montréal, working within the René Doyon's team in Montreal. And for this poster, we wanted to present a reanalysis of espresso data of LHS 1140 with the line-by-line framework. So I guess a lot of you are familiar with the LHS 1140 system, a famous system with two transiting super-Earth around an M4.5 dwarf. The first one, LHS 1140b, on a 24-day orbit was discovered in 2017. Planet B resides in the habitable zone and is actually if you want, this system is the second closest with the transiting planet inside the habitable zone after the TRAPPIST-1 system. And in 2019, a second planet C on a shorter orbit was discovered. And here this schematic is definitely not to scale, just to show you a bit the architecture of the system with the size of the planet, their mass. For now, those planets with radius and mass are thought to be genuine rocky super-Earth. You will see later on that that might not be actually true for planet B. So in 2020, the system was revisited by Lilo Box et al. Using espresso data and tests. So thanks to Etienne, on Monday, who presented this new line-by-line precision radial velocity method. Here I summarize into two key points. So the line-by-line at its core, we measure radial velocity on each and individual spectral line using the Bucci method. There are different implementations. It was first explored by Xavier Dumus at Geneva University in 2018. And the second key point is when we measure all those velocities, here on the right, I'm showing an histogram of those velocities for Barnard star observed with Spirou. We have 16,000 velocity. We can construct the histogram of those velocity and readily identify the bad ones, the bad lines that have velocities that are a few sigma away from the average one. Those bad lines can be, those outliers can arise from various sources, whether they are telluric residuals, detector artifacts, cosmic rays, but you just don't want to include them into the final average velocity. So the LBL, similarly to template matching, fully exploit the radial velocity content of a stellar spectrum. In the line-by-line paper, we demonstrated that it outperforms CCF in the near-infrared, mostly because in the near-infrared we have more spectral outliers. But also we showed for HARPS data of Proxima that it also outperforms CCF for M dwarfs because M dwarfs have more RV content. Their spectrum is characterized with molecular lines, often lines that are blended together. And so you really want to take the full spectrum into consideration to obtain the most precise RV measurement possible. We applied the LBL on espresso data. So it's exactly the same data set as presented in Lilo Box, so 116 spectra. In Lilo Box, the velocities were derived using a cross-correlation function. So here I'm just writing CCF, but just keep in mind those are published values, and we do not include additional observations. So this is really a reanalysis of existing data. And what we obtain is that the radial velocity from LBL have 3 times less dispersion than the CCF one. As you can see in this figure, it's the normalized error. You can already see that the distribution from LBL in blue is more Gaussian-like, sorry. But CCF, you can see that there are some outliers that are a few sigma away from the mean. So these are the, we perform a Bayesian analysis to measure the planetary signal of planet B and C. As you can see, I can just show the figure and let it talk by itself. The LBL are in blue, published values from CCF are in red. And you can already see that CCF, it's much more tighter to the orbital signal of the planet. And I can summarize the improvement into 4 key points. First one, with LBL, the RV uncertainty is reduced by a factor 2. So 50 centimeter per second instead of 1 meter per second with CCF. Second point, at the end of the orbital fit, we end up with 53 centimeter per second residual RMS compared to almost 2 meters per second with the CCF derived velocity. And that has a huge implication for the mass, when we infer the mass of the planet. But most importantly, I think, is those LBL velocity, we do not detect any kind of extra white noise. And usually we assume we detect 1 meter per second stellar jitter, and we just assume it's stellar activity. But in this case, for this particularly quiet star, we do not see any extra white noise needed in the data. And since this is a Bayesian analysis, if we don't need to increase artificially the error bars, in the end, we were able to measure an improvement of about 50% on the mass of planet B and C using the same data set. Yeah, I'm sorry, these are transits. It's a EPRV conference, but since we had such a nice detection of the mass improvement, we also wanted to improve the radius of the planet. And so we had an extra test sector data, but also 3 unpublished Spitzer data that were available in the archive that were out of proprietary period. And so we performed a joint fit of the transit data with the LBL radial velocity to obtain the most accurate measurement of both mass and radius of the planets. And so here in the mass radius diagram, I'm showing in green the 1 and 2 sigma posterior for planet B. Purple is for planet C, and I'm also showing with squares and circles the previous values from Ment et al. And Lilo Box et al. I'm showing both because they were derived with different sets of instruments, so they do not are not exactly compatible with one or the other. The picture is not really changing for planet C. So what we see is planet C is still consistent with genuine rocky super Earth. But now for planet B, planet B is now above the Earth-like sequence. So it kind of left off the Earth-like sequence and ended up in a portion of the MR diagram that corresponds to volatile rich objects. And so for planet B with such precision on radius, I'm showing below. So we obtained for both planets a 2% relative uncertainty for radius, about 3.5% relative uncertainty on the mass. And so the picture is completely different for planet B. That might now be one of the best characterized super Earth known in terms of mass and radius with the RV method, essentially. And since it is in the habitable zone, that might be one of the best, or at least I think it's the best candidate water world known to date. So yeah, so in summary, the LBL method is an outlier resistant method for precision radial velocity. It outperforms CCF in the near infrared and for M dwarfs. It performs similarly to template matching also. LBL analysis of existing espresso data of LHS 1140 resulted in a 50% improvement of the mass of the planet. And the habitable zone planet LHS 1140b is now compatible with a volatile rich object and could be, depending on the amount of CO2 and greenhouse effect of its atmosphere, can be either a snowball or an aquaplanet, a planet with a frozen or a liquid water surface that will need to be determined in the future. So just want to finish and say that the LBL code is publicly available on GitHub. It's working with Espresso, ARPS, ARPS North, Carmenes, Spirou, NIRPS. And so if you want to check out and reanalyze your data set, or you can also contact us if you have any questions. So thank you for your attention.
Wonderful job, perfectly on time. We have time for a question.
Hi, first of all, fantastic work, and the LBL velocities look incredible. Did you use the same activity modeling as in the original paper, or could it be that part of the improvement is also because of an improved activity modeling?
It's a similar analysis, so it's a really simple quasi-periodic Gaussian process. Since the rotation period is known from photometry, from M-Earth photometry, we just applied directly the model on the RV data and did not use polate Fmax like it was done in the paper. So the signal is it's really strong. So as you saw at the end, we have 50 centimeter per second RMS. So it was really like 3-component model, like planet B, C, and the 130-day period.
Okay, thank you.
Thanks.
Okay, let's thank Charles again for a wonderful talk and a wonderful poster.